Let's go ahead and start. What we're going to move on today is the first peripheral that really allows you to talk to external devices. So you buy your microprocessors because they have some GPIO, but those GPIO just don't turn pins on and off. They form communications interfaces that talk to other processors, talk to other peripherals. If you've talked to any of the embedded systems students, they are using SPI or I2C interfaces to talk to accelerometers, real-time clocks, memory, all these different fun things that don't live on your processor, but that you can buy from DigiKey and allow you to actually expand the capabilities of your system. So at first, we're going to talk a little bit just generally about communication, and then we will go into the UART, which is the Universal Asynchronous Receive and Transmit. That's the most simple communication peripheral that you have. So, as I said, you have a large number of peripherals on the system that are meant to talk to other devices. When you're looking at communication interfaces, you can have a UART, I2C, SPI, CAN. If you were on the electric car team, people use CAN bus all the time. Every different peripheral has a different speed, a different reliability, a different sort of packet size, and you can generally talk about any communication protocol as either being sort of serial or parallel. And parallel means that all of the bits of a message are sort of being transmitted at once. So if you think about like the RAM bus on your actual desktop computer, it's a 64-bit wide sort of bus. Or if you talk about something that is serial, it is sent sort of byte by byte by byte very fast. So you have sort of these two overall paradigms of what's sort of serial and what is sort of parallel. In general, we'll talk about for a given interface its bandwidth. And bandwidth is sort of the number of bits per second that it can support. So if I've got some sort of parallel interface and I've got 8 wires, and I can put 8 wires on the bus every second, I'm doing 8 bits per second, so 8 BPS. If I have a serial interface and I can put 1 bit on the bus, but I do it 8 times a second, I do it at 8 hertz, I also have 8 bits per second. And so what the trade-off is here is, do I want a parallel interface so that I can dump a lot of data onto, but maybe costs me more wires, or do I want a serial interface that I can only put 1 bit at a time, but maybe I can bang out that serial interface really, really fast? And honestly, when it comes to computers, microprocessors, sort of serial interfaces have really won out because of the speed at which these devices can communicate. When was the last time anyone plugged up an LPT cable to a printer? If anyone remembers what an LPT cable is. So printers used to have these big, fat, parallel interfaces. See, Bill and I are some of the older guys here, so we know what we're talking about. Big, fat, parallel interfaces, and you just plug them in. And the parallel interface, if you can do it fast, can dump more data because it's all parallel. But serial interfaces honestly have really won out on your mobile computing and on your microprocessor because it requires less pins. It just requires less pins, and pins mean more area. Pins mean more cost. So your USB is just going to have a transmit and a data and a power and a ground line. It's got sort of 4 pins, and it doesn't need that much more. So we can talk about the difference between serial and parallel, but really serial is just sort of where it's at. Another thing we can talk about in communication interfaces is whether something is half duplex or full duplex. And what that distinction means is whether something is both transmitting and receiving at the same time. So if you've got like an old kid walkie-talkie, you can't talk while someone else is on the channel. So it's half duplex. You can either transmit or you can either receive at the same time. Something that is full duplex means you can do both at the same time. So you can both receive and transmit at the same line. So if you have a transmit line line and the receive line, and they each have their own buffer, they can work at the same time. So just sort of a naming convention for you. And the way sort of a full duplex connection would work is that there's a dedicated transmit line and a dedicated receive line on each peripheral, and they each have their own buffers. So this is a block diagram of a SPI interface, which we'll cover next. But a SPI interface is there's a common clock line. There's data coming out from the master into the slave, and data coming out of the slave into the master, and they each have their own rotating buffer. So as bits come out of here, they end up here, and as bits come out of here, they end up there. So these two devices can exchange information at the same time. They actually have to exchange information at the same time, given the way they're set up. But this is an example of something that would be a full duplex connection, because both parties can talk at the same time. A half duplex connection would be an example of like an I squared C connection. So I squared C will be sort of the next second interface that we talk about. On an I squared C connection, there is one clock line and one data line that is shared with all of the peripherals on the bus. So this is back to your old walkie-talkie example where they have a common clock line that synchronizes transmissions, but only one data line that everyone uses. So if I'm transmitting to Darren and I'm using the data line, he can't then use the data line to talk back to me at the same time. So this is an example of what would be like a half duplex connection. Questions on this distinction? You can imagine there will be an exam question that says, describe the difference between half duplex and full duplex communications. Provide an example of what each might be. Sidebar on that, this material is not on the exam that is coming up, not next Monday, but the following Monday. So you have a pretty good gap here between the end of the exam on materials and actual exam 1, because I'm letting you finish up lab 2. But this goes on the next exam material. Michael.
Is that cell phone call being full duplex?
Yes, in the modern instance now it's VoIP. So like I can hear you and talk to you at the same time.
Yeah.
That could be that'd be a fine one. Travis, yeah.
So for exam 1, is lab 2 kind of like the culmination of the information that's on
Yeah, so exam 1, if you look I think I've posted the study guide for exam 1. Exam 1 is lectures. It's the lectures through interrupts. I think that's lecture 4. So it's lecture 1 through 4, and it's labs 1 and 2, and it's assignments 1 and 2. Like all of that is exam 1. All right, let's talk about the UART or the USART peripheral. The USART is what is on your device, and it's a UART that actually has synchronous capability. So on any microprocessor you ever purchase, there will be a UART on that processor. And UART stands for Universal Asynchronous Receive and Transmit. Your processor might also have a USART, which is a Universal Synchronous Asynchronous Receive Transmit. It's basically a UART that can also do synchronous communications. And we'll get into what I mean between synchronous and asynchronous communications. But every processor is going to have one of these. So when you boot up an Arduino and you talk to it over the serial port, you are talking to it over its UART. When you program an Arduino, it's over its UART. The most basic simple interface to make two things talk is over a UART, because you're just throwing bits at one another, and you agree on the clock, and you're able to read it out. So when we're looking at the data sheet or in the reference manual for this peripheral, it's going to say USART, but we're going to ignore sort of the S capabilities for now. We're going to ignore the synchronous capabilities for now. We will come back to those synchronous capabilities when we do the SPI lecture, but don't get confused. I'm talking about the same device. I'm just talking about its asynchronous capabilities. So as we go through all of the processors, all of the peripherals on the processor, because this peripheral has like two major modes it can be in, asynchronous and synchronous. That means it has a ton of configuration information, meaning it has all the configuration stuff needed for asynchronous operation and all the configuration stuff needed for synchronous operation. There's a ton of registers. There's a ton of registers and fields needed to modify for this device, but for the UART operation, the asynchronous operation, the default behavior is going to be pretty much what you need. So there's going to be a lot. When you look at the registers for this peripheral, don't freak out. Because you're like, oh my God, there's like 10 things I have to configure. There's 10 things you have to configure if you want to do everything, but we're not going to do that. There is also a UART peripheral in the Gecko. It's the same device, but they just disabled all the S stuff, all the synchronous stuff. So just so you can make that distinction clear. The internal hardware on the UART is pretty straightforward. There are two pins. There's a transmit pin, which means that data is leaving the peripheral, and there's a receive pin, which means that data is coming into the peripheral. There's no clock lines, there's no ability to synchronize transmissions, there's just a transmit pin and a receive pin. That's why it's asynchronous, because there's not a clock that we're all agreeing to. Because there's not a clock, basically when you start transmission, the person, or the device, not transmitting to a person, that you transmit to has to really get their timing down correctly. So the fundamental thing on a UART is that two parties agree on a clock. They agree on a frequency to sample that, a transmission frequency, but they don't share a clock. So it's like if Kira and I said, I'm going to give you 8 bits a second, and then when I say go, she starts reading 8 bits a second. Now there's nothing to keep our tempo the same. There's no maestro that's going to keep us in time together. We're just hoping that internally we have the same rhythm and the same timing. So one fundamental problem is that if our notions of time internally are off between the two parties, it will lead to inaccurate results. You will sample the signal at the wrong time, and you'll get the wrong result. So Nick and I are transmitting at 10 hertz, and he's slightly off because maybe his processor's a little weird, and he's actually like reading it like 10 or 11. Maybe that's okay, but if he's up at 100 hertz, we're at completely different time intervals, and so we're going to perceive different signals. So one thing that you can do to alleviate this is that the UART protocol allows for a parity bit, so you have 1 bit of error checking. So you can detect 1 bit of error if it occurs, but if you've got a really messed up signal, that's not going to help you at all. It won't help you even recover the error. What is that? This is the internal hardware of the UART, and I think it's pretty important to kind of understand this diagram, because once you understand the diagram, then you understand why I'm going to tell you to talk to all the registers that you need to talk to. So with any device, it's hanging here off the peripheral bus. All these registers are memory mapped, and it has, as you would expect, a control and status register. And the status is going to tell you, am I transmitting, am I receiving, have I overflowed, have I underflowed, like what the heck is going on. The control is going to set up the bus rate and the baud rate and the number of bits I'm setting and all that fun stuff. Down here, what you can see is that there's a transmit buffer and a transmit shift register. In a communication interface, because timing is so important, you don't write directly to the transmit buffer. Because let's say your processor's in the middle of writing and something gets interrupted, or there's a delay on the peripheral bus, and only half of this stuff gets written. So there are buffers, there are 2-level FIFOs that you write to first. And so the idea is that you write to the FIFO, and then it copies down, finally into the transmit register. So these are the bits right here in the shift register that actually go out onto the pin. So this is a buffer that allows you to actually put a couple of messages in it at once, but also isolates you from any sort of interactions here on the bus. Because the idea is that, well, maybe I mess up transmitting to one register, but when it copies, at least it'll copy in correctly to that shift register. Same thing with the receive register. You see down here, we've got the receive pin, and if you follow your data around to your shift register, it gets clocked into the receive register. And then it gets copied up into the buffer, and the buffer is where you actually read it from. So the buffers provide you two capabilities. It isolates you from the bus. It makes it a little more reliable to write to the device. And it actually gives you a buffer so that you can receive multiple messages at the same time. So in this device, you can technically transmit 3 things at once, because you can have one message here in the shift register and 2 messages in the buffer. At the same way for the receive side, you can keep one message here and 2 messages here before the entire receive side is filled up, and when a new message comes in, it either gets clobbered or gets dropped because there's no place to put the data. So the buffers do a variety of functions here. Final thing is that as part of the control and the status, you have a baud rate generator. When we talk about the speed of a UART interface, when we talk about bits per second, we're talking about the baud rate. So we're talking about the, I don't know why baud stands for bits, we're literally talking about the number of bits per second. So if it's 9600 baud, then that means it's 9600 bits per second. And I think it's really supposed to mean like symbols per second. But that's the general idea. Questions on this, because this is important to understand. And if you understand the hardware diagram, you'll understand why you have to write to all the registers that you need to write to make this work. Okay. You can talk to these shift registers directly. Don't. Just put it in the buffer, let the processor do its job. Or let the peripheral do its job. The way that a UART packet, let's talk about packet structure. The way that it looks on either the transmit or the receive wire is this. The data line is idle high. So when it's not in use, the pin's idle high. And the pin's idle high because if you pull them down the ground and someone pulls high, then you actually draw a current. Maybe there's a pull-up resistor. They just idle high. When one party wants to transmit, it issues a start bit. So it issues a start bit by pulling the data line low for, let's say, 1 cycle. Now there's no real clock here, but it's the amount of time that we believe 1 cycle is, because both transmitting and receiving parties have agreed to the amount of time. So if Kevin's trying to send me a message and we've agreed to, to send a bit every second, he would hold up a flag or pull the line low for 1 second, and then I would start reading the message. So the idea is that after you hold this low for, let's say, 1 period, the next 8 or 9 bits are the message, or is the message. It depends on the structure. Generally, UART packets are 9 or 8 bits. You can make them 9 bits. You can also make them have a parity bit. And I think even on this one, you can set sort of the number of bits that you want. But the idea is that you pull the clock low, then a certain agreed upon number of bits come out, and then if you want, there's also a parity bit at the end. So who remembers what parity is? Bill, what's parity? Right? So what does parity help you do, though?
It looks at the number of bits that are transmitted and sets the parity bit to make the number odd.
Right, so in an even or odd parity, you either want an even or odd number of 1s or 0s, just basically depending on how you set it up. And the parity bit is set to make that calculation either even or odd. So if I'm doing even parity, where I'm counting 1s, and I count up all the 1s and I get 9, then I know there was an error. I don't know where the error was, but I know that an error existed. So now I can talk back to my other peripheral and say, hey man, like that was a bad message, give me another one. The transmission stops once you've sent all of your data and that you pull the bus back high. So you release the bus, you pull it back high, and that's a stop bit, and that's what stops the transmission. And that completes the transaction. Yeah, Travis.
Sorry, I was just confused, or wondering if there's a reason that the brackets are there, or just
I think on this figure, the brackets are there to indicate they are optional. So I have 0 through 15 here, and I probably wrote that for a right reason. This graphic probably is this is just an example. So the idea in this particular picture is that I think you could probably convert this down to like a minimum of 5 bits, but these are optional. So the parity bit is always optional, and the width of sort of the message can be adjusted. So there's no like universal worldwide rule that says UART transmissions look like this. The UART sort of standard, if there is one, is that you and I agree on the clock. There's a start bit, a stop bit, a parity bit, and a certain message width. You can extend it to whatever length you want. So starts in a high position, pull it low for a start, bang out my data, leave it high to let you know when I'm done. So that's how you can know how long all the data is. Now, the baud rate, so a couple sort of key words here that we want to talk about. The baud rate is the rate of transmission that we talk about. You can set the baud rate to be whatever you like, but there are some common ones that are used in most microprocessors. So the slowest and the default one is 9600, so 9,600 bits per second. The next one is 55600 or 57600, 57,600. And the last one is 115,200, so 115200. So if you see in a forum somewhere or on a data sheet somewhere, and it says, baud is 9600, that's what it's talking about. I've honestly never seen a device communicate at a baud rate other than these. Like, there's like a 1200 one, or maybe it's.
Are these like the agreed upon rates that you're talking about?
Yeah, so these are the agreed upon rates that two devices will communicate at. So both peripherals are configured to talk at those rates before they even begin talking. Those are the most common rates, and I've never used a device that didn't communicate at one of those 3 rates, just because they're so common. And you can kind of see it's like super low speed, medium speed, high speed. Like if you want to think about it that way, that's the general sort of parameters that you've got there. Data bits are the number of data bits that you are sending. Generally, it's either 8 or 9. Again, ours can be configured, but it's really just 8 or 9. Parity, it can be disabled, it can be even, it can be odd. The stop bit, so you can have a certain number of stop bits, and that basically means like the length of time that we consider stop to be. So you can sort of have like half of a period for a stop bit, or you can have sort of 2 whole bit periods for your stop bit. I've never seen it anything but 1. So the way that all this information gets communicated is someone will say, well, this peripheral is configured to work at 9600 8N1. And you will see this all the time. And what that means is 9600 baud, 8-bit messages, no parity in 1 stop bit. So at the same time, you can say, I'm going to do at 57600, 8N1. So it's 8 data bits, no parity, 1 stop bit. Again, I have never communicated with a peripheral that wasn't 8N1. It's the easy, stupid default that everyone can implement. You can, given the speed at 9600, you can actually implement this interface in software with just interrupts and regular GPIO. So you have these capabilities in this peripheral, but I've really never seen it stray beyond 8 bits, no parity, one stop bit. All right, here's a question to think about. Why wouldn't I always transmit at the fastest rate? So, Joe, why do you think I wouldn't always transmit at the fastest rate? transmitting slow. Maybe there's better work I could be doing. I mean, there's a factor of 100 here, roughly. Well, there's a factor of 10. There's a factor of 10, 15 here. And so maybe I want to transmit as fast as possible just so I can get that data out and I can get on to other things. The fundamental thing about this is that, again, there's no agreed upon clock. So the faster we go, the more in sync we have to be in sampling the data. So what we're going to see in a little bit is that the faster you go, the more error creeps into your communication. One thing in talking about UART and serial and all these other words that are kind of used when talking about this interface. So begin rant. The word serial is not the same as UART, is not the same as RS-232, is not the same as TTL. So you will one day go on some embedded processor forum and they'll talk about all these words and they will use them interchangeably. They are not interchangeable because some of these words mean a peripheral and some of these words mean a voltage level or a signaling interface. So you might hear someone say, oh, I use a serial interface on my Arduino. Well, actually what you used was the UART on your chip. That UART, if it's connected to your computer, is not directly connected to your computer on most Arduinos. There's a level translator chip in there that takes the UART packet and turns it into a USB packet. So if you use the serial interface on your processor, it's something that's 3 to 5 volts. If your computer has an old serial interface on it, it's operating at like the RS-232 voltage levels, and that serial interface is going to be 15 to negative 15 volts. So even though you use the word serial for both things, it is not the same thing. So if you connected to your Arduino to the PC through the serial port, no, you didn't. You connected your UART to a level translator chip that turned it into USB that then talked to your computer. There's always going to be some sort of converter in here. So you need to be really specific when you're talking about serial, because lots of communication methods are serial, but are you talking about the interface or are you talking about the voltage levels? And so where this comes up is someone like buys a microprocessor and they're like, oh, I've got a COM interface or a serial interface on my laptop, let me connect them. Well, your laptop's going to bang away at 15 to negative 15 bits, or volts, and it's going to blow up your processor. So whenever you're purchasing a part or you're looking at a peripheral that says it has a serial interface, or it talks at TTL levels, like I just ignore all of that until I get a real concrete explanation of what actual peripheral it is and what voltage levels the peripheral talk at. It may be the same sort of general framework of a start bit, a bunch of bits, and a stop bit, but if the voltage levels are completely off, you're not going to talk and you actually may fry the other device. So again, if you get two Arduinos and you connect their serial ports together, one may be a 5 volt part, the other may be a 3 volt part, and they may burn each other out. So when it comes to, if you're in Capstone or if you're buying parts and something says that it has a serial interface, be really, really wary until you figure out exactly what that means. Was that a question?
Yeah. Isn't that why you typically, that's why you typically see it, that PPI is sold as a standalone module you would connect between your microcontroller and whatever else you're going to be.
There are a couple reasons for that. So let me get, I don't have one in here. Let me get particular. So I gave away my FTDI cables to Kyle in the back, and he's got them. But here's the idea: is that this is a 3 volt Arduino. This particular chip has USB built in, so you can take an FTDI cable and use it to break out your USB connection and connect it directly to your computer. This is a 5 volt part, but it comes with this chip on it right here, which is the FTDI chip. You're basically either buying the chip on the board or the chip in the cable. And this is what allows you to plug directly into your computer. So yes, like this one has USB built in, but you still need a cable to communicate between them. So there's less parts on here, he's slightly bit cheaper. This one, you don't need a special cable, you just need a normal USB cable, but he has to have a regular chip. And this chip is directly connected to the UART on here. So pins 0 and 1, which are the serial port for the USB, are directly connected to the UART on this processor. Different processors. This is a 32U4, this is a 28P. Same Atmel family, but they're completely different in the way they handle sort of serial communication. And so, and that's the thing, like people will say, like a lot of times people throw out terms, they'll say, let's use the FTDI cable, or use the USB cable, use the serial port. Like, you need to know sort of more details about what's actually going on. Travis?
So would you say that serial is a more general term for these specific implementations? Or is serial itself a specific implementation?
The word serial is a non-specific term. People use it often to mean the UART. They use it. They say they use that to mean like the UART interface because that is the one asynchronous sort of serial interface. Serial is a more general term. If you had a 1995 Linux server, you would also plug in a monitor and a keyboard to the serial terminal. Like your keyboards before they were USB were serial interfaces. So the word serial is more generic, and that's what I'm saying. Like I think some people interpret it as a specific thing, where it doesn't denote anything beyond bits are coming in order. That's all it really means. All right, back to the little the parts that are on your gecko. So again, I talked about that you don't directly talk to the shift register. So the idea is that your message eventually ends up here and goes bit by bit by bit by bit out from a shift register. So the transmit pin is directly connected to this little bit here, and it just shift, and that's how your bits go out. There is a 2-level FIFO that comes off the peripheral bus, holds one message and then another message, and along sort of with those messages are also sort of the control for those configurations. So you have a double FIFO here that will buffer your messages so you can send multiple messages at once, but also it isolates you from any interaction or sort of any noise on the bus. The reverse side is true. You have a receive register where the physical external pin is connected to this bit here, and as data is received, it gets shifted in, so that finally the message lives here. If there's any status that deals with the message, it gets copied up, and copied up to make sure that once the bits are received, they're quickly pulled out of the shift register so more stuff can be received. And also it gives you a little bit of buffer so that when a message occurs, you don't have to immediately respond to that message. So this allows the processor about sort of 2 messages before it has to interact. So, now for the interactive part. Pull up the reference manual, go to page 488, look at the number of different interrupts that the UART supports. So we just finished talking about interrupts in the last lecture. Interrupts are going to be a dominating feature from here on. Take a second, look at the various interrupts that this device supports. So if you're looking at that slide, there's a lot of different interrupts. So transmit buffer overflow. That means that you've tried to put more data in the transmit buffer than we have. The buffer is half empty. You might, if you're putting a lot of data in there, you might want to know when the buffer is half empty, when it's completely empty. A receive buffer underflow. So what the heck might cause a receive buffer underflow? Carrie, any other thoughts? Because with a receive buffer, well, what might underflow? If overflow means I got too much stuff, right? What would underflow mean? It took too much. So in a receive buffer underflow, you try to read the received buffer when there's nothing there. So you try to pull data from the received buffer when the processor knows that there's no information there. So you try to pull some stuff out of the received buffer. The received buffer is already empty. Received buffer underflow. You need to know if overflow is too much data. So basically, my buffers have filled up and you haven't taken any data away. I'm completely full of data. There's nothing else I can do. And then there are some ones that deal with flow control, about a collision being detected, whether there was an error in parity, all these fun things. The major ones that we're going to deal with would just sort of be data available and the buffer empty. I mean, you can make this super interrupt driven where it's like, it's half empty, better put in some more data. Oh, it's completely empty. Let me put in a ton of data. Like you can be as aggressive as you want filling up these buffers, but in general, you really just kind of care, is my data gone and has data been received? So you don't have to deal with all of these different levels. Okay? General questions on just what I talked about with UART. Stop bits, start bits, baud, and parity, because we're going to go into the actual communication rate in a second. Okay? As I mentioned before, there's no synchronizing clock between these two devices, which means that they both have to agree on the same data rate. And if they're off, if they're misaligned, then there are going to be errors in transmission. So the two parameters in this particular peripheral that you care about in setting baud rate are called clock divider. So again, we're going to have the peripheral clock that we divide by some manner, and there's an oversample parameter. So like in the timer, there was a prescaler. In the UART, there's a clock divider. Same idea. Here, there's an additional parameter of oversample. And so the idea is that instead of sampling one, let's say, bit period, I might sample 4 times and take the majority of that sample. So you can oversample your signal to ensure that you read it correctly. And what we're going to see is that there's a trade-off between the speed that you talk at and the amount that you can oversample. So if you open up the application note for the UART, and all the application notes are available on the Schoology site, you will see either one of these equations that describe if I want a certain baud rate, it's based upon these parameters. Now, the main difference between the application note and the reference manual is how they describe the clock divider. In the application note, it uses div to mean the actual amount it's divided by. It's divided by 1, it's divided by 4, it's divided by 17, whatever it might be. In the reference manual, it uses clock div, and it talks about the value of the entire register. So these div bits are actually like shifted over by 8, so you can think them as being multiplied by like 256. So the reference manual talks about some number and then just magically multiplies it by 256. And you'll say to yourself, well, why the heck did you do that? And it did that because it's talking about the whole register. Here, in this note, we're going to talk about the actual amount that the clock is divided by. It's a subtle but sort of important difference. One talks about the value of the entire register because the bits are already shifted, and we're talking about the actual amount that you're divided by. So what you can see here is that the baud rate that you want is a function of the high-frequency peripheral clock. So what value is that? How do we know what value that clock is? Kyle, how do I know what the high-frequency clock is? Give me one way I can figure it out. So that's not a bad answer. Remember in assignment 2 where I asked you to ask the processor what the clock is? You just ask the processor what the clock is because it's configured to something. The data sheet's not going to say the high frequency clock is 14 megahertz forever and all time. you need to act, because it's based on configuration. So for our examples here, because the default in your software is 14 megahertz, we're going to use 14 megahertz, but in your real system, you should always look it up. You should always look it up and ask and make sure it is 14 megahertz. That frequency gets divided by how much you oversample it. So if I take the frequency and I want to sample each bit 4 times, that means I cut my baud rate down by 4. It gets cut down even further by the amount you naturally divide the clock. So you're going to naturally divide the clock by some amount. So you take the high frequency clock, you divide it by your oversampling, you divide it by the amount of clock that you divide it by. If you wanted to rearrange and figure out what the actual divisor bits are, you can rearrange the equation and get this. Because generally, you know what baud rate is. You know my peripheral needs to talk at 9600. And you also might say to yourself, well, depending on how fast the transmission is, I'm going to oversample a certain amount just to be safe. So generally, baud rate, oversample, and frequency clock are sort of set or they're known, and all you have to do is calculate the clock divisor. So the effective clock divisor for that frequency and that oversample. Questions on this? Here's what I mean when I talk about the difference between div and clock div. So the reference manual, when it uses this equation, it uses the value of this entire register. So there are 6 zeros in here that you don't care about because it's just shifted over. So if you look in the reference manual, when it talks about how much you're dividing it by given the clock div, it will say USART clock div divided by 256. Whereas we use clock div divided by 4. And the difference in that factor, that 264 factor, that factor of 64 is just the difference of whether I care about, we talk about this particular div, or I talk about the entire sort of register. Travis?
Why did they shift it over like that?
No idea. I have no idea. One, because it can. Maybe there's a thought that in the future they'll put some bits here to do other stuff. But I have no idea why you would automatically shift it over like this, and I have no idea why. Well, I know why. I don't know why the reference manual and the application note aren't common in the way they describe the clock rate. And the reason they're not common is because 2 different people wrote them. They're on different versions. No one's going to make sure that the 700-page document really comports with a 30-page document. So it's just an error in documentation. And you can imagine, if you're not paying attention, you can mistake this number for this number, and your baud rate's going to be off by a factor of like 64. It's just going to be wrong. Or 32 to the clock. Okay. 2 people that have to talk have to agree on the baud rate. So how accurate, and each system is going to generate its own baud rate. It's going to have its own clocks. It's going to have its own crystals. It's going to have not the magical crystals that heal you, but the magical crystals that make clocks. It's going to have its own setups with clock divisors. Like, it's not necessarily going to be a gecko talking to a gecko where they have the exact same setup. It could be a gecko talking to a pit or an atmail or something else. So how close do these devices need to be so that they can successfully communicate? The answer is ask Dr. Blaney. In general, if you want to know the exact perfect answer about how common these 2 need to be, Dr. Blaney can tell you. I'm going to tell you that the baud rates between them need to be within 1 to 2%. So the question earlier, why wouldn't I transmit at the full rate the entire time, is because the higher I get, that 1 or 2% becomes harder and harder to reach. That it becomes more and more likely that we're going to be off by that much. So the way that the balancing act that you have is that the higher the baud rate, the less oversampling that you have. Because increasing oversampling and increasing baud rate lowers my effective frequencies. So you can't do both at the same time. So as you can see here, the more, so the oversample is set by the OVS bits. So OVS oversample. The lower the OVS number, the more oversampling you do. It's kind of counterintuitive, but I guess I understand why they do it. So if OVS is 0, then you're sampling multiple times per bit. So you get 16 sort of samples before the bits. As you increase oversample, as you increase the OVS number, you sample less and less. But the trade-off between the two is that the more that you oversample, the less you can actually push your baud rate. So here's the idea, though. The reason that there are fixed and common baud rates is because those generally represent the ones with, let's say, the least amount of error, or the error that is most acceptable. A couple things about this document. It was obviously written not in the US because they use commas where periods should be. So flip your brain around, get used to that. This is the only section of this document that does that. Everything else uses periods. So this is an editorial nightmare. But what you can see is that given a certain clock frequency, so if you assume that the peripheral clock is 4 megahertz, if you want a 600 baud and you set the clock divisor to 415, what you actually get is 599.88, which means you're off by 0.02%. Well, great, you've got a really sort of accurate clock there. But as you push the baud rate, you get more and more inaccurate because you can only divide your clock by a fixed amount, and you can only oversample in fixed amounts. So these are not continuous variables. They're discrete variables, and so you can only set certain frequencies. So you can see that depending on how much oversampling you have, it changes the amount of error that you have, but it also kind of limits your frequency. Like the more that I oversample, or the less that I oversample, the more error I'm going to get. Or the less I oversample at the higher frequency, the better my error is going to be. Important takeaway. You can set lots of different baud rates. They may or may not work out to be what you want because of fixed clocks and fixed oversample rates. I'm not going to make you fill out this table in an exam bill.
I was just wondering why there's negative values in there as it's a positive error.
Because it's underneath. It's underneath the desired one. So like this one here. Yeah. So you want 230,000 and you got 250,000. So you're above by 8%. So here's a problem for you. Assume that the peripheral clock is 14 megahertz and you want to do 16 oversamples. Look in the reference manual and figure out what bits, what clock values do you need to do this. So this is not in the reference manual. This is just a straight calculator question. So if you want 14 megahertz and you're going to oversample by 16, so just put the number 16 here, what clock divider value should you use to get 9600? So the idea is you determine that you want 9600 baud, you're going to do a 16 oversample to be accurate. What is the value that you put in clock divider? So go ahead and... So something I would expect you to be able to do is to do this calculation, and if I said I desired a certain baud rate, what is the divisor value that you're going to put in? I want you to calculate 360.588, recognizing that that number has to go to a real register. You either need to round it up or round it down. Your particular choice. Once you have rounded it up or rounded it down, you then calculate the effective baud rate. So the effective baud rate is 9615. That means If it's 9615, I wanted 9600, I am above by 0.15. Ben?
Would it make sense to round to the closest number to get the lower error?
You don't know if you're overshooting or undershooting. I mean, yes, okay, round to the closest number. So you're saying if this is 360.99999, like, yeah, I would round up. But the issue is whether, like, that fractional difference matters. Michael?
There's be formulas that we need to memorize to like answer the test question.
On your exams, I will give you the reference manual. So when you have your exam, I will give you reference manual and I will give you data sheets. So do not spend your time. So don't spend your time in the exam memorizing equations. So sidebar, the labs are really practical. The labs are what bits do I put in this register? What do I do? Like, how do I write code? The exam is more conceptual in terms of how do these interfaces work? How do they communicate? There's a little bit of calculation like this, but I'm not having you write code on the exam. Like I'm examining you when you write your labs. That's how you do your code. But the exams are going to be more of what happens to a UART interface when I increase the baud rate. Like why don't they communicate well? It's more of a conceptual question than it is do the calc. Now you might have these calculations. I'm pretty sure I'm probably going to ask you one of these, but I would not have you memorize the equations. This is not a universal equation. There's no point to that. Travis.
So, is this equation in the reference manual?
It is in the reference manual, but it is, again, remember, it is dealing with it deals with the full register value and not the actual value that you put in.
So you give us like the whole reference manual?
Yeah, so what I did last year was, everybody logs on to these machines, not your personal ones, but these machines. I look at everyone's desktop, I put documents on your desktop, and I shut off the internet. And then you got 10 hours. And that's what but that's like you get the docs. Like you know in CS201, like they gave you a certain amount of docs, a certain amount of, like I'm gonna give you the documents. Like that's kind of gonna be it. So please don't spend your time memorizing what bit lives where. Spend your time understanding that there are interrupt flags, that there are interrupt enables, how you go about enabling an interrupt. I will say that if you think that you can just Google your way through the exam by using a reference manual, you're going to run out of time and you're going to fail. Like you need to know the answers, and then you need to use the reference manual like to support your answers, like to go find a particular value or find a particular field. If you don't know what you're looking for, it's not Googleable. Like this course is not Googleable. It's all about a particular department. Sound good? All right, so the effective error on this is 0.15, which means it is going to be pretty accurate. Now, this value that you calculated here, 360, which is hex 168. The important thing about this is that the number 168 goes here. So you would take 168 and you would shift it over 5 bits to put it here. So that is the fundamental difference between when I say what's the clock divisor versus when the reference manual talks about the entire register. So the reference manual is going to say set this register equal to something that is 32 times that number. What I am saying to you is put the number 168 right here, which means you need to take that number, you need to shift it over 5 bits, you need to OR it into the register, or you can just actually equals it since there's nothing else in this register. That's an important point. I don't want you to get confused on that. Yeah, let's do that. So go to page 145. Look at all the different registers that you've got. Find the registers that deal with oversampling. Find the registers that tell the device whether it's an asynchronous or synchronous mode. Find the registers that set up the parity, the start, and the stop bits. And find the registers that enable receive and transmit. This one is tricky because there's a lot of things involved in receiving transmit. But let's take a good sort of 2 minutes. Let me see if I can divide this up. So I want this table here, U3, to do the bottom question. Okay? I want U4 over there to do this middle question. And I'll just put everybody sort of on the back row up here on this top question. So back row here, left table here, right table here. So figure out what registers and then where those registers control those things. And I'll give everybody a couple minutes to do that. So when you want to disable transmission, you do it in the command register. So much like the timer where it was start timer, stop timer, here you have a receive enable, a transmit enable in the command register. There are fields that look very similar in the route register, but they're not these ones. In the route register, it's like enabling alternate functions. There is also receive tri-state and transmit tri-state. There are other flags that deal with RX and TX that look really, really similar, but are not these bits here. So if you want to enable, like logically enable transmission, you do RX enable. If you want to logically enable, transmission, it's TX. If you want to logically enable reception, you do RX enable. Before you do all of that, you have to configure everything else. You have to turn the pins on, you have to make the pins inputs or outputs, and blah, 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 blah. So if you want to deal with oversampling and synchronous asynchronous, you're sitting here in control in the OBS register and the sync register. If you want to control parity, stop, and data, you're in the frame register with stop and parity and data. As we go through all these peripherals, you're going to have to figure out all these registers and all these fields, and you're going to have to write code to put bits in there. It's going to get tedious. So on Lab 2, that's why there's a function called modify bit field, because you want to be able to write modified bit field UART control, and then put in 3 for 2 bits, put in 5 for the offset, and put in the value that you want. You don't want to have to manually write that code each time that modifies arbitrary bit fields. You really want to use that Lab 2 function called modify bit field that will modify an arbitrary bit field of an arbitrary register. It's going to make your life so much easier going forward. So please take the time to implement it, and if you can't implement it, please ask me. You got the parity bits, and then you got the receive and transmit bits down there in command. One thing to talk about is, given the relationship between the sync bit, the loop bit, and the master bit, it puts the device in a different mode. So sync governs whether it's synchronous or asynchronous. So it's either a UART or something else. That something else is either an I2C or a SPI interface, and we will talk about those later. So this table right here shows you how to set these up on all of the different modes. Loopback is a mode that is really useful for testing. So loopback means I'm going to internally connect my receive and transmit pins. So that way, if I can transmit to myself and receive from myself, then hopefully I can talk to someone else. If you can't talk to yourself, which I do all the time, then you can't talk to anyone else. So a very fundamental test on an interface is to talk to another device, is to talk to yourself to make sure that the data is going out correctly. This master bit deals with I2C protocols, and we'll talk about that later. Also sort of with SPI protocols, we'll talk about that later. But basically this is to say, given this configuration of bits, these are what all of your pins do. Here's a summary, and then after this, we'll start up on Monday about all the different pins that you have. These are the UART or the USART registers that you care about. You care about control because that configures, that's a great word. That configures the oversampling, the clock divider. That's where all the control stuff, actually clock divider is its own thing. That configures the oversampling and the synchronous mode. Command is where you actually tell it, hey, go transmit, hey, go receive. Status is where all the flags are. Am I overflow, underflow? Is my buffer empty? Have I just finished transmitting? Have I had a collision? Everything that's in status. Clock divide is where you actually divide the clock value. And here I'm referencing the entire register. Transmit and receive buffers. Remember, you don't want to talk to the shift register directly because you may have a collision on the bus. It may start transmitting in the middle of your write. So you want to talk to the buffer and make sure it's copied down correctly into your peripheral. IF is where all of your interrupt flags are. The status flags, something in a status flag may cause an interrupt flag, but they are not necessarily related. So the status just may be status information, where IF refers to a particular interrupt has occurred. And status is going to be kept live, where if an interrupt flag is asserted, and it's ever been asserted, it will always stay that way. So status is sort of your more live information, and IF is just, well, I've seen these flags over my lifetime. What we will talk about on Monday is the route register. So, just as a preview, the GPIO can serve multiple purposes. And you have to, and each peripheral can be mapped to various GPIO. So it's not fixed. You have to set up a route register to say, for this particular peripheral, I want these pins routed to it. And it's kind of annoying, and it's kind of complicated, but basically, for a particular GPIO, you have to set a route register such that the alternate functionality for that GPIO, so the default functionality is on, off, input, output. If you want alternate functionality, which is I'm a SPI, I'm a UART, I'm an I2C, if you want that alternate functionality to come down, you need to use the route register. And we'll talk about the route register and going into the reference manual and looking up everything, and we'll talk about that on Monday. So you've got about an hour left. Let me just stop this. You got about an hour left, and let's work on